and then we're going to experiment with them in the lab. So the whole concept is called the collision theory, and that's what chapter or reading guide 18 was on. So first, particles must collide. They must collide with proper orientation. So it's like two things are coming together, and the bond is supposed to form between two nitrogens. When they collide, and you collide a nitrogen and oxygen together, then that orientation is incorrect. And then if they don't collide with enough oomph, they'll never break the bonds that are present within them. So must break bonds of the reactants, because they have to free themselves up to recombine to form products. So that's kind of what these three main concepts are referring to. And so I want you to give me an analogy to baseball. This is the part we skipped yesterday on the web quest. So think about baseball, okay? Get in the mood, virtual reality here. And then when you hit the ball, that's simulating which of the three parts of the collision theory? They must collide, right? Okay, what does a foul ball represent probably? Improper orientation. So what does a, skyrocketed home run represent? Proper orientation, okay? What does a bunt represent? Insufficient energy. Insufficient, so maybe it's not going to, maybe they'll get, catcher gets up, because the catcher's the best person. I was a catcher. Same. They rule the roost there, so they would throw him out first base, and then maybe weird home run. So you can see the collision theory. You can really, it's analogous to quite a few things. Or how to get a date, right? We all learned that yesterday. I know you're going to try that sometime today, okay? Yes, I mean, you have to in chemistry to get a date. It's required. Okay. Nobody other than chemists. So these things we've seen 3 times, I think, before now, right? You're like, this is old news, I got this. But I want you to tell me what happens when you add a catalyst to this reaction. So if this reaction, first of all, before we get there, is this reaction right here indicating an endothermic or an exothermic reaction? Exothermic, so it's going down. What would happen if I added a catalyst?
One thing would be shorter. It would go in the same spot.
So the pink arrow would be smaller, like this. So the first parts, the beginning and the end, are the same. Those are not affected. It's just what's happening in the middle. So which reaction would happen faster, the blue reaction or the green reaction? Right. So as a catalyst means it's going to speed up the reaction and make it go faster. So would the time be shorter or longer for that reaction to occur? Shorter. So it's happening faster means it's overcoming the bond and creating the process faster. Second one is definitely endothermic reaction, right? Looking at the comparing the activation energy, this activation energy to this activation energy, which one looks like it's going to take longer? That one. Which one? The endothermic one. Why? It's like, oh my gosh, I've got so much energy to put into this reaction and fall in there. Okay, so the bigger the activation energy, maybe the longer the reaction, or maybe it will never happen because we don't have enough energy to get that energy overcome. Okay, so that's review. And then I got 2 more things to review. Okay, this is on your paper. These are questions that help me figure out how you connect your pieces of your puzzle, okay? So take a couple minutes and start those with the person next to you. And just explain or describe in accordance with the collision theory.
Fewer reactants, which means there won't be as many collisions, which means, yeah.
No, they're all true. You have to tell them why. Basically,
Oh, yeah. Gases react more quickly than solids as well.
You are writing down
because
descriptors.
gases move quicker than solids.
Words for that.
Solids
With more energy, higher
pressure.
energy of motion. Energy of motion.
Gases have higher kinetic, which means there's more collisions in the reactor with gases. And then solids.
No, there's water. On the right. Yeah, exactly.
So what did you call?
Are we doing? Are we on B yet? We're on C.
Decreasing the temperature will decrease the reaction rate.
And temperature can really get much. Temperature, like the higher temperature, the faster it goes into more kinetic energy, so it makes less. It's like if it's colder, then it will go really fast.
Okay. Yeah. And there might not be enough energy, and also. Actually, yeah.
Yeah.
I'm scrolling down a little bit. There's 2 and 3. Go like that.
Temperature and pressure. Volume. Yeah. What does a catalyst do? It pairs up reactions at the right configuration.
Alright, I will go right back down. Let's talk about the first couple. Yes, sir.
So for C, right?
Mhm.
So if we get to the temperature being cold, wouldn't you want to move faster to get to the pressure?
Yeah, but so I want you to tell me what happens to the rate. So describe why it occurs. So why is it slowing down, something like that. So let's talk about those right now, okay? So let's start with A. Lowering the concentration of the reactants will decrease the reaction rate. That is a true statement, yes? Why, Hayden? Kind of start me off. Let's go baby steps. Tell me the very first thing that happens and why it happens. Okay, so less particles means less collisions, right? So remember, you're always relating it to the collision theory, so you're probably going to say the word collision at some point in time. All right, so lowering concentration means there's less particles, means there's less collisions. Lesser rate, right? There you go. Perfect. I want to see the baby steps to get there. Gases react more quickly than solids. We know this is a true statement. Sally, go for it. Okay. Okay, so I'm going to say solids have low surface area, maybe something like that, whereas gases have greater surface area, and they increase in surface area means you can collide more. Give me one more thing, Matt and Audrey.
Gases have higher kinetic energy.
Okay, so they're also going to be colliding with probably correct. What's that term for energy? That word that goes in front of energy. Activation energy, right? Sufficient activation energy. So I'm also going to add to that gases have higher kinetic energy because they're moving around faster. So they will likely meet activation energy needed. So I'm just abbreviating this for you, okay? Decreasing the temperature will cause a decrease in reaction rate. So we know that's a true statement. Audrey, go for it.
So if there's like less temperature, then there won't be as much kinetic energy, so they won't collide as hard.
Okay, so there's actually 2 parts to this one. So make sure you represent this in a twofold representation. Decreasing temperature decreases kinetic energy. So that's going to do one. What did you say first?
That they won't collide as hard.
So I'm going to say they won't collide with.
Another.
Right. They won't. I'm not sure what I'm writing. Won't collide with enough activation energy. And then secondly, they probably, since they're moving slower, do you think they're going to collide frequently? No. So the second part of this, and this is the important one, anytime you mention temperature, you must mention both things that it does. Doesn't mean activation energy because they're moving slow, so there's not enough force in their reaction. And then they collide less frequently. And so if they collide less frequently, then they're just not going to react as often, so the reaction rate slows way down. So that's the one that just is very special, has 2 parts. Okay, so shout them out for me. Jaylen, tell me one way to increase a reaction rate. Increase the temperature is one. Tal, give me another one. Ask Caroline. Okay, cool. Never mind, you got it. Increase the concentration. Remember, brackets mean concentration, right? Okay. Kathleen, tell me another one. Increase surface area. What else, Danielle? Decrease the volume of the container so they're sitting in a closer containment with each other. Anything else? Thank you. Okay. Add a catalyst. Okay. And then we all know, we just briefly talked about this, what does a catalyst do? That actually speeds up the rate of the reaction. Max.
Like lowers the activation.
Lowers the activation energy, so it's more, you can overcome it very easily. Okay, that's basically what you learned yesterday by yourself. What? Okay. So, but it's common sense, right? And you guys wrote down these notes.
Yeah.
Yes. Okay. Here is, I just accidentally did the same thing. This is, so I've got this slide to talk about for rates, and then we're going to do our lab, okay? So, this basically, as what I'm telling you is, rate has a specific way of expressing it in chemistry, versus like, how did you drive? You drove to school this morning at what rate? Okay. So but at what rate? Slow is not a rate. So 30 miles an hour, 55 miles an hour, 150 miles an hour, whatever you
I
do.
took a plane.
15. I ran to school. I was running about 2 miles an hour. Okay. So that's distance over time. Don't laugh at me because I'm slow. Okay. So that's distance over time. But for chemistry, we don't really go with distance. We're dealing with chemicals, right? So it doesn't make sense for us to talk about distance. It makes sense for us to talk about particles and concentrations. So what we're looking at is the change in quantity over the change in time, and that will give us an indication of the rate of a reaction. And the quantity can be in reference to either the quantity of the reactants or the quantity of products made per time. And that's what our lab is dealing with. So that's kind of what your quantities are going to be looking like, you know, some amount. So when we say quantity, we are generally going to be using molarity. This is big M. And then for time, we'll probably use seconds, maybe minutes. So these will be likely our units for most of our rates. Bless you. And so whenever we see this on a graph, I want you to kind of explain what this graph, why the graph looks like it does when I scroll down in just a second. Yeah.
What is it?
This equals rate. So the rate of a reaction equals a change in quantity over change in time. Yeah. Most of the time, it might be molarity over minute, depending on how fast it is. So you can probably imagine, if I start off with reactants, what happens to the quantity of reactants over time? They decrease. Why? Because they get consumed to make products. So what should happen to the product concentration over time? They should increase, right? Okay, so look at this graph. Give yourself a sketch. Pretty easy graph to sketch. Axes are important. Please sketch the axes and all. And then label which is reactants and products based on what you just said. You're going to have to draw a graph, not exactly like this, but close to it, so I want you to have at least a reference point. You do not have to label the axes with numbers, just the what it's talking about. Axes. So at time 0, what did I start off with at time 0? 0.1 what? Molar concentration. So my concentration of the reactants were 0.1 molar, and my concentration of products were 0. So over time, as the reactants get consumed, they go down, 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 down. And then all of a sudden, as they start to go down, well, you're like, law of conservation of mass, gotta make something, making products. So then they slowly go up, 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 up. And they might cross, in this graph they do cross, in other graphs they may not cross. But regardless, you're gonna come to the point where eventually the reactants stop, or they start going down, 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 and then they might level out. And this could continue. they'll level out and not change concentration anymore. And then products at the same time, when the reactants level out, the products will also level out. And so this is what we're dealing with today, this changing concentration over time. And then if you looked at, who looked into part 2 of the web quest already? Maybe saw a couple. Okay, it's called equilibrium. And equilibrium is what we're going to talk about more on Friday, so tomorrow. And where that equilibrium occurs, whenever this part right here, the graph occurs. When the concentrations are not changing, so they're at a stable state. So this is equilibrium. Okie dokie? Okay, so pull out a piece of paper for your lab. I'm going to give you a brief what we're doing. So this lab requires us to talk about one tiny bit of biology before we go back, so you remember what color change is supposed to occur, okay? So our reaction is between iodate, it's potassium iodate, but it's just the iodate one I'm concerned about, and then sodium bisulfite, that's bisulfite, okay? But the sodium bisulfite is in starch. It's an acidified starch, so do not smell it. It burns your nose hairs. Okay. Whenever, and this might remind you of maybe the diffusion baggie lab if you did in biology. Iodine and starch, when they get together, what color do they make? Purple, black, right? Okay, so that's it. Whenever you see a purple, black, blue, whatever dark color, that is telling you that you have made the product, that whatever product we're making, and that reaction is done. Now you've got to watch it like a hawk, because you can blink and it will turn. Okay, so don't blink. Got it? Requirement for the lab, do not blink. So you don't need a stopwatch. You can use your phone. That's totally fine. Most of us have 100 milliliter beakers. Some of us are going to have 80s. It does not matter. If you don't have enough of things, just let me know at the beginning of the lab. You will need 2 graduated cylinders, okay? Because one reactant's going to go in one the whole time. The other reactant's going to go in the other the whole time. Because if you start putting them in the same one, they're going to start reacting before you're ready. Okay, so don't contaminate your samples. When you get to a point, I'm going to say, okay, designate one person to be the hot plate person, and that means you're going to make a hot bath and heat up your reaction so that you can see what happens when to the rate when the heat is increased, and then vice versa for ice. So you're going to share those at your lab station with everybody at your lab station. Other than that, I didn't label the beakers for you. I mean the flasks that I put the chemicals in, but solution A is the iodate. It is the clear one. Solution B is the starch, sodium bisulfite, and it is the blurry one. B is blurry, okay? B is blurry. Don't mix them up. Other than that, I will let you know if I want to run 2 hot trials or 1 hot trial. It just depends on how far we get, okay? So same lab groups as last time. Let's get the party started. I'll let you get your goggles on. It's called the iodine clock reaction. I'll help you get started as soon as you get back there. Leave your web quest on your desk if you did not. Leave your web quest on your desk.
So it's called what?
Iodine clock reaction.
What reaction?
Iodine clock reaction. All the way. Iodine clock reactions. Iodine clock reactions.